Any other homework questions? Anything you want me to go through? Last time we did an example like this. We had a cantilever beam connected to the wall on the right side and a distributed load like this. And this was 1,000 newtons per meter. Okay, and so we only had one cut. When we did that cut, we had a triangular distributed load on our cut piece. The difficulty was, the little wrinkle that came up then was, so if you're cutting a piece like this, you still have a triangular distributed load on that piece, but it doesn't have a maximum value of 1,000. And so the highest point of that right triangle, you have to express as a function of x. Okay, so the height of this point comes from the equation for that line. Okay, and then you have to, from that point on, everything you do is the same as a triangular distributed load when you're calculating external loads, but you just have to use these functions of x for everything. And, this is x. Okay, so what if you saw this? So there's no reason it has to be cantilevered on the right. I'm just going to do that to make the problem look similar for everything except the one change I want to make. So what if you have a cantilever connected on the right like this and a triangular distributed load like that? Okay. I mean, there's nothing at first glance that makes you think that's obviously going to be way trickier or anything. Okay, bless you. But when you make your cut here, that's, bless you. Yeah. Anybody else? Let's try to get this all out right now. Okay, so this is 3 meters long. That's what we had before. And so our x for our cut is valid for anything between 0 and 3. Okay, so let's do our cut. So we have a piece like this, and let's give this a value, 1,000. And we're leaving out this part of the beam. And this distributed load looks like this. Okay, and then you have your internal loads. But now this is way more of a pain. And that's because in this case that we did last time, when we make our cut, our distributed load is still a triangle. Okay? When it's facing the other direction like this, and we're cutting off the point of the triangle instead of the high point of the triangle, we make that shape a trapezoid. Okay? So the left over distributed load shape is a trapezoid. Okay. It's not impossible to do. What you have, then you'll break it up into a right triangle sitting on top of a uniform distributed load. And you can treat it as two separate distributed loads. Okay. Maybe we'll do an example of that at some point. But you can do it, but at the least, it's tedious. Okay. So here's what I recommend doing in the case that you see something like this. Instead, walk around to the other side of the beam. Okay, so once you do that, here's what you see. Now you have the cantilever on the left. And your triangle is facing this way, so when you do your cuts, the distributed load is going to be a triangle. Okay, and so you can come up with your function, calculate the internal loads at every point along this beam the same way we did before. Yeah.
Since the domain doesn't cover endpoints, are we allowed to ignore the wall?
Well, at the wall and at the end, once you, we're just going to assume that these are well-behaved functions. So you mean ignore the, okay. So like when you do the cut, could you do the cut without going all the way to the wall so that you couldn't, so you didn't have to calculate those external loads? Is that what you're talking about? The problem is, no, you can't, because, so let's say that we did our cut like, so here's the beam. And let's say we did our cut like this, just skip that contact point, went out to some arbitrary x value. This is some infinitesimal amount, so that distance is still x. Okay, but the problem is now your free body diagram of this, you don't have those external loads, but you have something worse over there. You have internal loads from the surrounding material. So here you'd have your, your T1, V1, M1. And over here, you're trying to calculate your T2, V2, M2. So you've jumped out of the frying pan and into the fire. So that's why we always go all the way to the end, is so that, bless you, on the left side, we always go all the way to the end, the left side, the left end, because we want to deal with external loads and not these internal loads. Okay. All right, let's do, let me do another one, and then where I put a few different things in, and then next time, whether it's today or next class, I'll just give you time to work through the steps.
So with that one we just did, instead of flipping it around, could we just do our cuts going from the other side and use negative x coordinates?
Yeah, you can do that too.
Okay.
I would recommend, I mean, it's a way to avoid dumb mistakes to just do it the same way every time. I think that's the only benefit of always working from left to right, you know. But yes, and actually, it would be good practice for understanding that sign convention, getting used to that sign convention. Yep, definitely you can. All right, so let's. Say we have, so let's put a pin joint at the middle of this beam and a roller at the left end. And a distributed load on this side that goes to a maximum of 500 newtons per meter. And let's make this length 1 meter and this length 1 meter. And let's say the mass of the beam is 10 kilograms. And we want to calculate these internal loads. All right, so what's the first step?
Calculate the external.
External loads, yep. And so for that, this is just a really simple rigid body problem. At the midpoint, we have, I'll call that RB. We also have the weight of the whole thing of 98.1. And then we have a force up of, I'll call that RA from the roller. And then the distributed load, this right triangle, it has a length of 1 meter, a height of 500. The centroid location is 2/3 of that length from the point. And so that's just 0.6 repeating. And the area, the point force representing this, is 1 times 500 divided by 2, so 250 newtons. And so this force is over here at 250. I always put my about point at the left end point for the cuts. When you're doing the external loads, I mean, this is just a rigid body problem, so feel free to put it wherever you want for that. I'm going to put it here for this one. And you always could write out the whole table to do this if you prefer. I'm just going to, since this is just a horizontal beam, I'm just going to think about it in terms of directions of rotation and moment arms and stuff. Okay, so first, this force RA. Well, let's do Newton's second law first. So we have 0 RA plus 0 negative 250 plus 0 negative 98.1 plus RBX RBY is equal to zeros. We can't, I guess we can solve for RBX is equal to 0. I keep forgetting to put horizontal stuff on this. Am I going to do it now? Yeah, let's. Let's put a force of 1,000 newtons over here. So that changes the free body diagram. So we got this. And then in Newton's second law, we have negative 1,000, 0. So RBX is equal to positive 1,000. And the second equation, the y equation, says RA plus RBY is equal to 348.1. And we'll just have to set that aside and come back to it after we do the moment equation. Any questions about what I'm doing so far? And then the moment equation with my about point at the center. The 1,000, does that produce a moment? No, it's on these horizontal beams, it's only the vertical components of stuff. RA, what's the moment arm of RA?
Negative direction.
Well, yeah, I mean, so if we're just doing it sort of with this intuitive way, we'll just think of all the moment arms as positive, and then we'll just think about the direction of rotation for the sign. So that's going to be 1, the moment arm. And that force is RA. And now is that rotation clockwise or counterclockwise around the center? Clockwise, so we'll take the negative. Then we got the 250. What's the moment arm of the 250 around the center?
1/3.
1/3, yep. And the force is 250. And would that force make it rotate clockwise or counterclockwise? Counter, so we'll take the plus. And then we have the weight force. That's no moment arm. So this one goes away. And then we have, bless you.
Oh my gosh, excuse me.
This is going to be my last warning, everybody. Come on. So then we have RB. Well, it's only the RBY that would matter, but it has 0 moment arm, so that also goes away. These are equal to 0, so we have negative RA plus 0.333 times 250 is 83.3. And this is equal to 0. So RA is 83.3. And now we can plug that back in here, and RBY is 264.76. I'll just call it 77. Okay, so we have that our RA is 83.3, and our RB is positive 1,000, positive 264.77. So now if you want to draw a free body diagram of the whole thing before we get into it. We have a force at the center of 1,000, a force down at the center, nope, up, of 264.77, a force up at the left of 83.3, repeating. And then we have a distributed load, this triangular distributed load, like this. And then we have the distributed load for the weight force. The total weight is 98.1. The total length is 2. So divide 98.1 by 2 and you get this uniform distributed load of 449.05. And what was that triangular value? Was that, did I say 500? So this goes up to a value of 500 here. Okay. The most common mistake that people make is thinking, okay, we have our free body diagram for the external load, and it has a point force representing the triangular distributed load and a point force representing the weight, okay? And so then when they go to the cuts, they leave those as point forces and do the problem that way. And that's why I keep saying, remember, you don't represent your distributed load as point forces until after you've chosen the cut, okay? We could do it once we chose, you know, that our free body is going to be the whole thing like this. But we can't use those representations now when we go to different cuts. We have to make the cut and then after that represent these as point forces. Are you with me on that? Okay, so how many cutoff points do we have? We have the endpoints. And now we're looking for anywhere else where, yes?
You're missing 1,000 force on the left.
Yes, thank you. Thank you.
Was about to fly off into
That's true. Yeah. So now we're looking for places between the two endpoints where there are point forces, point couples, or a distributed load function that changes. How many points like that are there? Just one. It all happens at the same place. And so how many cuts are we going to have to make? Yeah, right. We're just going to choose an endpoint between those first two red dots and an endpoint between the second two red dots. Okay, so cut 1. This is for x values between 0 and 1. Remember that our cuts always go all the way from the left end. I'm going to erase this just because it's going to get cluttered otherwise, but so what that means is we're leaving off all of this. You know. So we have the 1,000 Newton force going this way. the 83.3 repeating force up there. We have the uniform distributed load. And we have the triangular distributed load. And then we have T, V, and M. Okay, any questions about that? Well, the height of this triangular distributed load, well, let me do the easy one first. This uniform one is still the same. But the height of this triangular distributed load isn't going to be 500 anymore. Okay, so what we have to do is come up with, this thing has a length of x. So we have to come up with a function for that line, that diagonal line, the hypotenuse, as a function of x. So we can do that from the original picture. It has a rise of 500 and a run of 1. And when x is equal to 0 on the left side, the y-intercept is 0. So this function is going to be 500 over 1 times x plus 0. Or in other words, it's just going to be 500x. Okay, but before we can do the calculations, we have to represent those distributed loads as point forces. We can do it now that we've chosen the body that we're isolating. So here's the triangle. It has a length of x and a height of 500x. Since it has a length of x, this distance is 2x over 3. And the area of this triangle is the base times the height divided by 2. So we get 250x squared. And so now I'll redraw this. So now we have the point force up of 83.3 repeating, the force to the left of 1,000. I didn't draw the rectangular distributed load, but it's a rectangle with a height of 49.05, and I'm going to draw it. Who do I think I am? Okay, so the centroid is in the middle. So this distance is x over 2. The height is 490.5. The base is x. And so the area is 490.5x.
49.05.
Oh, yeah. Okay. So this point force is in the middle. It's 49.05x. This point force is a little to the right of there, and it has a magnitude of 250 x squared. And then we have the internal loads T, V, and M. And now we can go Newton's second law. So we have, I guess I'll combine these two forces on the left. We have negative 1,000, positive 83.3 repeating, plus, okay, so remember that the expression is, so the arrow is the unit vector and the expression is what you're multiplying by that unit vector. So the arrow for this 49.05x is in the negative y direction. So this is 0, negative 49.05x. The 250x squared is also in the negative y direction. So 0, negative 250x squared. And then plus t minus v, I'll just put them in one vector, is equal to zeros. So you get that T is equal to positive 1,000. That's the internal tension. V is equal to negative 250x squared minus 49.05x plus 83.3 repeating. Any questions about those? And then the moment equation. Now for the cuts, we always put the about point at the left end. So the 1,000 and the 83.3 don't produce any moments. The 49.05, is that clockwise or counterclockwise? Clockwise, so we have negative. The moment arm for that was x over 2. The force is 49.05x. Then the 250x squared, is that clockwise or counterclockwise? Clockwise, so we got another negative. The moment arm is 2x over 3. The force magnitude is 250x squared. Then we have the contributions we always do from the internal loads, plus m minus vx is equal to 0. And so we have m is equal to v times x plus, that is 166.6 repeating x cubed plus 24.525 x squared. And now we have to plug in the v. So we're just going to multiply x to this expression for v that we had already. So m is equal to negative 250x cubed minus 49.05x squared plus 83.3 repeating x plus 166.6 repeating x cubed plus 24.525 x squared. And now just combine terms. Here are our x cubes. Here are our x squares. And so we get m is equal to negative 83.3 repeating x cubed minus 24.525 x squared plus 83.3 repeating x. And that is it. For cut one. Cut two is going to be easier though because we don't have the triangular distributed load cut in the middle, you know, so it's not going to depend on x anymore. Might as well, I mean, I haven't stated this like officially yet, but we're starting to get the sense that dm dx is always going to be equal to v if things go right. So let's just check that. Dm dx is negative 250 x squared. Yes. The second term is negative 49.05x. Yes. Derivative of the third one, 83.3 repeating. Yes, so that worked out. You can catch a lot of mistakes calculating your moments that way, your bending moment. And then we're expecting negative dv dx to equal q. Well, we have to think a little bit about what q is first. So q is the total distributed load function on this cut. So we have one distributed load function that's 500x. We have another distributed load function that's 49.05. So our total q is going to be 500x plus 49.05. Okay, you just add those two functions up. So negative dv dx is positive 500x. So that one matches. Minus 49.05, plus 49.05, we're taking negative dv dx. So that one matches. Derivative of that is 0. And so we feel good about these relationships. So now cut 2. This is for x's between 1 meter and 2 meters. And so we have the 1,000 to the left, the 83.3 repeating up. We have a triangular distributed load that doesn't get all the way to the end. We have a weight force. Well, I guess since I'm drawing the distributed loads, that distributed load for the weight force is still this, and it has a magnitude of 49.05. And then we have this point force here of, what did we get for that? 1,264.77.
With the distributed loads, once we figure out what they are as a function of x, can we just write them down as a point force with that x variable?
Yeah.
Okay.
As long as the distributed load continues to the to your new cut right endpoint, you know. So like we're going to see that we don't have that anymore with the triangular distributed load. Now we're just going to have a number for that.
Oh, okay.
You know what I mean? Because the right end doesn't cut in the middle of that triangle anymore.
Oh, okay, so that'll just be the point force from the very, very first. part
Yes,
we got.
that's right.
Okay.
That's right,
And
exactly.
then the weight force will still be.
Yes.
Distributed.
Perfect, yep. Okay, so 1,000, what was this again? I forgot. Damn it. 264.77. And then we have the internal loads. It can get pretty cluttered looking. So now I'll draw it again. Stupid computer. This computer can almost make it 50 minutes without doing that, but not quite.
Makes me want to try and fix it.
Yeah. It makes me lazy because what I just have to do eventually is go talk to IT and say, like, this doesn't work with the programs anymore. And they take this and put it in a box and take another one out of a different box and give it to me. Okay, so here we have the point force, which was so for that triangular distributed load, we have a base of 1, a height of 500. So the total force is 250. And the distance from the end is 0.6 repeating. And then we have a point force from the weight, and that's going to be 49.05x. And then we have the forces from that pin joint, 1,264.77. And then T, V, and M. So Newton's second law says negative 1,000, positive 83.3 repeating, plus 0, negative 250, plus 0, negative 49.05, plus 1,000, 264.77, plus T, negative V, is equal to zeros. So T for this half is equal to 0. V is equal to 49.05. And now the moment equation, the about point is over here at the left. There's no moments from the 2 at the left. The 250, is that clockwise or counterclockwise? Clockwise, and so that is negative 166.6 repeating. The 49.05x, is that clockwise or counterclockwise? And what's the moment arm for that? Nope. X over 2. Yeah. So I don't know. It helps to draw out the shape. especially at the beginning. Yes.
So why does that minus 49.05 vector not have x in it? In Newton's second law.
Because I didn't put it in here. Thank you. Okay, so and that would have been a case where when we would have done the derivatives, we would have seen that mistake. Or we would have seen there was a mistake, and then you go back and find it. Okay, so what do we have? 264.77 minus 250 plus 83.3. So that's 98.1. So we have negative 49.05x plus 98.1. All right, so we got the first moment, then the 49.05x is negative with a moment arm of x over 2. Then this one, we only care about the y component for the moments. Is that y component clockwise or counterclockwise? Counter. And what's the moment arm for that?
X over 2?
Nope, that one is at 1. So the this point force, well, let's look at the original picture. That just comes from this pin joint, and that pin joint doesn't move. Okay, so that pin joint is just 1 meter from the end. So this is just going to be 264.77. And then we have plus m minus Vx is equal to 0. And so m is equal to V times x plus 24.525x squared plus 98.1 and then plus Vx, so minus 49.05 x squared plus 98.1 x. Oh, that's the Vx. So and so m is equal to negative 24.525 x squared plus 98.1 x plus 98.1. dm dx is equal to v. Now what's q in this case for this cut?
Just the weight.
That's right. This time that triangular distributed load doesn't count for that q function. And so all we have is a distributed load, a q function of 49.05. So negative dv dx is equal to 49.05. And
the final answer be minus 98.1? In the first line, you combine negative 166 and 264 to get positive 98.1?
Yep, you're right. Yep. And those constants on the moment is something that the derivative thing won't catch too, so. Thank you. Any questions about that? This is as ugly a problem as I'm going to give you.
Kind of cool how those, at least the simpler ones, work out to like totally make sense when you think about them.
Uh-huh.
Like the shear one.
Yeah, right. Yeah,
It's like,
and then,
it's the weight, but like minus however far along you are
Uh-huh.
along it.
yeah, yeah. And then when you get to deform, you're going to use these internal loads at these different points to calculate the stresses and strains. Okay, that's all.
No class Monday.
Yes, Veterans Day on Monday.
I really hope I remember that.
Well, if you don't,
I don't think you get in here.
unless you live in, where do you live? Then I'll tell.
Tappahannock Hopkins, about a Minnetonka, I'm 30 minutes away.
Okay, yeah, that wouldn't be so great to get here. If you live in Bloomington, it would be a nice little surprise.
Well, I live in Buffalo and I've driven out here before.
Yeah, that sucks.
2 hours, yeah.
Buffalo?
Yeah. Name me a good college that's any closer.
Huh.
My options are Hennepin or Anoka Ramsey, and they both kind of stink, especially for what you pay. I crash at my aunt's house. I drive out here the night before, so I don't